Welcome to the Mathematical Olympiad course, the first course on YouTube that's gonna cover everything there is to know about mathematical Olympiads. Today we're gonna cover the weighted AM-GM-HM inequality. That's gonna be awesome. Okay guys, so the weighted AM-GM-HM inequality is just a generalization of the regular AM-GM-HM inequality. It states that whenever we're given a sequence of positive real numbers, let's call those xi's, and some set of weights that are positive integers, I call them wi's right over here, then the following chain of inequalities hold. Well, first of all, the weighted arithmetic mean, which is, well, the sum of all those x's multiplied, where each and every one of those x's is multiplied by its assigned weight, yes? So w1 multiplied by x1, w2 multiplied by x2, and then wn multiplied by xn. And then we divide this entire sum by the sum of all of those weights we assign to every single one of those x's. That's the weighted arithmetic mean. That's going to be greater than or equal to the weighted geometric mean, which is the product of all of those x's, where each and every one of those x's is risen to the power of its assigned weight, and then we just raise the entire product to the power of 1 over the sum of all of those w's, so the reciprocal of the sum of all of the weights, and that's gonna be greater than or equal to the weighted harmonic mean, which is just the sum of all of the weights we assign to x's divided by the reciprocals of those x's, where each and every one of those reciprocals is multiplied by its assigned weight. And well, the nice thing here is that if I were to now set each and every one of those weights, so w1, w2, all the way up to wn, I would like to set it equal to 1, then what I will get is the weighted AM-GM will just kind of turn into the regular AM-GM. How is it so? Well, every single way is gonna just turn to 1. So I'm gonna be left with, in the numerator of this fraction, is just the sum of all the x's, yeah? And what I'm gonna be summing in the denominator is just a bunch of ones. Actually, those are gonna be n ones. So the the denominator is just gonna turn into n. So I'm just gonna be left with the sum of all of those x's divided by n, which is just the regular arithmetic mean. What about the geometric mean right over here? Well, this thing's will also look like the regular geometric mean when I say that all of the weights are equal to 1, because I'm going to be just taking the product of all of those x's to the power of 1 multiplied together, so that's just going to be the regular product of all the x's, and then I'm going to be raising that stuff to the power of the reciprocal of the sum of all the weights, but the sum of all the weights is just n, because there are n weights, and each and every one of those is equal to 1, so it's going to be just that's just going to be the power of 1 over n, so it's going to be the 1 over nth power of the product of all of the x's. That's just going to be the nth root of all the x's. That's just the geometric mean. And what about the harmonic mean? Is it gonna work just as well? Well, it absolutely will, because if I were to say that every single weight is equal to 1 right now, then the sum of weights in the numerator would be equal to a 1. The denominator would turn into, well, just the sum of all of the reciprocals of x's, and well, that would just, oh sorry, not 1 but n right here, actually 1 times n. So what we would get here is just n divided by the sum of the reciprocals of the x's, and that's just equal to the regular harmonic mean. And so this perfectly works. So what I would like to do now is, well, go on and prove those guys out. First of all, I would like to prove the AM-GM inequality and then the GM-HM inequality. Oh, I forgot to put the circle here. Let's go. Okay guys, so let's prove the weighted AM-GM inequality. We are supposed to prove this inequality right over here. So, well, first of all, let's maybe try and rewrite this entire thing that we have here on the left hand side of this inequality right over there, maybe in yellow, because why not? So we will get w1 multiplied by x1, then w2 multiplied by x2, x2, and then all the way up to wn multiplied by xn, and then all divided by the sum of our w's. But well, what we can do here is just interpret this multiplication we're doing here by those ways as just repeated addition of those x's we multiplied those w's by. So we just rewrite this entire thing as x1 plus all the way up to x1, this time I'm not mistaken, then x2 all the way up to x2, this time I was mistaken, and then we'll just be adding stuff until we get to xn, and then we will add xn a couple of times to itself. We will divide all of this stuff by those weights wn. However, now we will have w1 of those x's, we will have wn of those, well, wait, w2 of those x2s, and wn of those xn's. So what we can actually do here is just, well, apply the regular AM-GM inequality without the problem, because, well, we will have just w1 plus w2 plus all of the way up to wn of numbers in the numerator, and, well, w1 plus w2 up to wn in the denominator. And so this is just the arithmetic mean of all of those x1, 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 x2, 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 xn, xn, xn. And so it will all be greater than or equal to, well, a1 x1 multiplied by x1 w1 times, then x2 multiplied by x2 w2 times, and then all the way up to not wn but xn times wn times. That's gonna be w1 times, that's gonna be w2 times, that's gonna be wn times, and this entire thing is just gonna be risen to the power of the sum of those weights, because this is exactly what we are dividing the regular arithmetic mean by. So that's by the AM-GM inequality, w1 all over to wn. But we can just go on and rewrite each and every one of those multiplied this repeatedly multiplied x's as x1 to the w1, x2 to the w2, and xn to the wn. And well, this is exactly what we're supposed to prove, because this is just gonna be equal to x1 to w1 all the way up to xn to wn, all to the power of 1 over the sum from w1 up to wn. Okay guys, and now let's prove the weighted GM-HM inequality. So, well, once again I would like to just kind of rewrite the guy we have on the left hand side of this inequality in terms of just, well, repeated, this time not addition but repeated multiplication. So I would like to rewrite those x1 to the w1, x to the w2, and xn to the wn as x1 multiplied by itself a couple of times, yes, so that's gonna be the x1, and then multiplied by x2, which is gonna be multiplied by itself a couple of times. We're gonna be multiplying all of that stuff out until we get to xn and multiplied by itself a couple of times. And actually those couples of times gonna be just w1 for x1, then w2 for x2, and wn for xn. Then we're gonna be just raising this entire thing to the power of the sum of those w's pretty nicely, and that's gonna be greater than or equal to, by the regular AM-GM inequality, well, to the sum of all of those weights. So the reciprocal of the exponent we have here, that's gonna be just w1 all the way up to wn divided, or maybe I will do it, oh yeah, that's better, divided by the sum of the reciprocals of those numbers, so 1 over x1 plus 1 over x1 all the way to 1 over x1, and then 1 over x2 all the way up to 1 over x2, and then all the way up to 1 over xn, all the way up to 1 over xn. As you can see, those x1s will appear w1 times, those x2 will appear w2 twice, and then those xn's will appear w sub n times. So you can just go on and rewrite this entire thing, as the sum of all of the w's, so w1 up to wn all over w1 over x1 plus w2 over x2 all the way up to wn, sorry, not xn, but wn over xn. And that's exactly what we're supposed to prove. Okay guys, so let's get to the problem number 1. We are given 3 positive real numbers. I didn't write that they're positive real numbers, but just, trust me. A, b and c with a sum equal to 3, and we're supposed to prove that a to the b times b to the c times c to the a is less than or equal to 1. Man, I have such a sore throat right now. Okay, so, well, you should already see that a to the b, b to the c, c to the a, it looks a little bit like the weighted geometric mean with the small tweak, which is that we are not raising it to the power of 1 over the sum of weights, whatever those weights would be. Yeah, but I think we can do something about it, because what are the exponents we are raising those a, b, and c to? Well, those are just b, c, and a respectively. Well, that's pretty nice, because if we now interpret those a, b, and c as weights themselves, then we can just take the cube root of both sides of this inequality, yeah? And that's because, well, 1 over a plus b plus c, which is just 1 over the sum of all of the weights, is gonna be equal to a third. So what I would like to do now is just raise both sides of this inequality to the power of 1 over a plus b plus c, which is just the power of 1 over 3 because of the problem conditions. That's going to be less than or equal to the cube root of 1, which is equal to 1. And now, well, proving this inequality is absolutely sufficient, because it just about implies this inequality right over here that we had originally to prove. So let's go on and do this thing. Well, how can we use the AM-GM, the weighted AM-GM inequality for on this guy right over here? Well, we can just go on and estimate an upper bound for this expression, which is gonna look something like this. So, a to the b times b to the c times c to the a to the power of 1 over a plus b plus c is going to be less than or equal to, well, a multiplied by its weight, but its weight is b, so a times b, plus b times its weight, which is b times c, and then plus c times its weight, which is c times a, so just ca right there. Well, that's absolutely lovely, because now what we are only have to do here to achieve the weighted AM is to divide everything by the sum of the weights. And we're supposed to prove is going to be less than or equal to 1. Well, it's not going to be probably the easiest guy, but I have a neat trick, because if we were to rewrite this one as, let's say, a plus b plus c all over 3, well then, well, that's pretty interesting, because we are able to solve this kind of an inequality. I mean, just go on and multiply out both sides of this inequality, and what you're gonna end up with is 3 times AB plus 3 times BC plus 3 times C on the left hand side. On the right hand side is gonna be A plus B plus C all squared, but A plus B plus C squared is just gonna be A squared plus B squared plus C squared plus double AB plus double BC plus double CA. So we just go on and subtract those guys from this hand side without a problem, and so what we're gonna end up with is AB plus BC plus CA less than or equal to A squared plus B squared plus C squared. But now I can either use the regular AM-GM inequality, or if you see it, use the rearrangement inequality, which is gonna state that when I assume without loss of generality that A is gonna be greater than or equal to B, which is gonna be greater than or equal to C, well then it will directly imply this statement here. And if you don't know the rearrangement inequality, which by the way, if you don't, then the previous video on this channel is about it, so go and check it out. You could just say that a squared plus b squared all over 2 plus b squared plus c squared all over 2 plus c squared plus a squared all over 2, which is, by the way, equal to a squared plus b squared plus c squared is going to be greater than or equal to ab plus bc plus ca, and that's because, well, c squared plus a squared all over 2 is going to be greater than or equal to ac by the AM-GM, b squared plus c squared over 2 is going to be greater than or equal to bc, and a squared plus b squared is going to be greater than or equal to ab, but, well, it is all over 2. So when you just go on and sum those guys up, you end up with this inequality right over there, and, well, that's pretty much the end of the problem. Lovely. Okay guys, so the problem number 2. We are given 3, once again, positive real numbers, but I didn't write it here, but doesn't matter. A, B, and C such that the sum is equal to A1. We're supposed to prove that A to the A times C to the B times C to the C, and then, well, the cycling sum of it, let's say, is always less than or equal to 1 for all such A, B, and C. Awesome. So how are we supposed to do it? Well, we are supposed to estimate an upper bound on a sum of expressions that, well, do look pretty similar to the weighted geometric mean. And so I'm thinking, well, probably it would be a nice idea to use the weighted AM-GM inequality, especially that it's actually a video on this inequality, so probably this is what I'm getting at. Okay, so, well, I would like to actually try and get some kind of an upper bound on every single one of those guys right here. Well, how do I do that? You see, if I take, for example, this guy underlined right over there, and I will write him here, so a to the a, b to the b, c to the c, then I will raise it to the power of 1 over a plus b plus c, so it looks like a geometric mean, but oh wait, the nice thing is that a, b, c is actually equal to 1, so I don't really have to care about this exponent at all. That's gonna be less than or equal to, and now we use the weighted AM-GM inequality, so a multiplied by its weight is just gonna be a times a, so a squared, then b by its weight is b squared, and c by its weight is c squared, all divided by a plus b plus c, which is sum of the weights. So that was the first term in our sum. Let's now move on to the second one. So that's gonna be a to the power of b, b to the power of c, and not a but c to the power of a, everything to the power of 1 over a plus b plus c, but that's just to the power of 1 over 1, so I'm not even writing it down. That's going to be less than or equal to a by its weight, which is ab, plus b times its weight is bc, plus c times its weight it's ca, then all over the sum of weight, which is a plus b plus c. I'm not really deleting this a plus b plus c from those denominators, even though it's equal to 1. You will see why in a few seconds. So now the third term, that's going to be a to the c, b to the a, and c to the b. That's going to be less than or equal to, well, once again, a times its weight plus b times its weight plus c times its weight, and then everything divided by the sum of those weights. Beautifully. So now what can we do here? Well, we're actually trying to estimate an upper bound on the entire sum of all of those terms. So maybe it would be a nice idea to try and sum all of those upper bounds and try whether we will get anything from that. So that would be a to the a, b to the b, c to the c, plus a to the b, b to the c, c to the a, and then plus a to the c, b to the a, c to the b is less than or equal to, and now that's going to be, well, a squared plus b squared plus c squared, and then those guys right over here are actually the same, because as you can see, CB is here and here, BA is here and here, and AC is here and here. So we can just go on and pair those guys up, getting double AB plus double BC plus double AC. Pretty lovely. And now we divide everything, we now divide everything by a plus b plus c. Okay, but what is a squared plus b squared plus c squared plus double ab plus double bc plus double ac? Well, these things just a plus b plus c all squared. But, well, if now this upper bound is equal to a plus b plus c all squared divided by a plus b plus c, well, that's equal to just a plus b plus c, but that thing's equal to 1. And so we got our desired upper bound on the entire sum of those awfully looking terms. Lovely, let's go further. Okay guys, so for the last problem, the 1997 Croatia Mathematical Olympiad problem number 2. For distinct A, B and C that are, I wanted to say positive reals, we're supposed to prove that a to the a, b to the b to the c is always greater, strictly greater, not greater than or equal to a to the b, b to the c, c to the a. Awesome. So how are we supposed to do it? Well, I would like to, well, as you might have already guessed, use the way AM-GM-HM Inequality because, well, that's the video about this inequality. That's a video about this inequality. Well, how can we use it here? Well, the nice thing is that the AM-GM-HM inequality kind of puts this GM in the middle, yes? So we can use this system of inequalities, this chain of inequalities, to prove both a lower bound for this geometric mean and also an upper bound for this geometric mean. Well, that's absolutely awesome. And that's because, you see, what we can do is use that chain of inequalities to both get some kind of a lower bound for this expression and some kind of an upper bound for this expression, and then compare those bounds because, well, if we manage to prove that the lower bound for this guy is greater than the upper bound for this guy, well, then truly and surely this guy is gonna be greater than this guy always. So let's go on and do this then. First of all, how can we get a lower bound for a to the a, b to the b, c to the c? So let's write a to the a, b to the b, c to the c. Well, if you want something to be less than that stuff, let's say less than or equal to, well, then that would be definitely and absolutely the weighted harmonic mean. But that would just be a plus b plus c all over. And now, well, the reciprocals, but each and every one of those reciprocals would be multiplied by the weight it's assigned to. So that would be just, well, a over a, b over b plus, I want to say c over c, which is just 1 plus 1 plus 1, which is gonna be 3. And a nice thing is that maybe I will say it later. But yeah, we have a lovely lower bound for a to the a, b to the b, c to the c. Now let's consider some kind of an upper bound for a to the b, b to the c, c to the a to the b, a to the b, b to the c, and c to the a. Yeah, that's gonna be less than or equal to by the AM-GM inequality is gonna be a times its weight, so a times b plus b times its weight, which is b times c, plus c times its weight, which is c times a. Here once again we're interpreting a, b, and c as the weights of a, b, and c, so or rather b, c, and a as weights of a, b, and c respectively, and then we divide it by a plus b plus c, which is lovely. So now if we want to prove that a to the a to the a, b to the b, c to the c is greater than a to the b, b to the c, c to the a, we actually have to prove that a plus b plus c all over 3 is going to be strictly greater than ab plus bc plus ca. Yeah, all over a plus b plus c. But there is no problem, we actually solved this particular inequality earlier on in this video. So what we will get is that in this video? No, in the previous video on the rearrangement inequality. So if we multiply both sides of this inequality out by the denominators, what we're gonna get is a squared plus b squared plus c squared plus double abc, plus double, not abc, plus ab double ac plus double bc is gonna be supposedly strictly greater than 3AB plus 3BC plus 3CA. Now we can just go on and cancel out those guys from here, getting A squared plus B squared plus C squared supposedly greater than or equal to AB plus BC plus CA. Well, strictly greater. Well, we see that it cannot be greater, it cannot be equal, those two sides cannot be equal to each other. That's because, well, it would only happen if, well, AB would be equal to A squared. Oh, sorry, what the hell just happened here? BC was equal to B squared and CA was equal to C squared. Well, that would only happen if A and B and C would all be equal to each other, but we are given in the problem statement that they are distinct numbers, and so it will never happen. But for the inequality itself, we'll just assume without laws of generality that A is going to be the greatest, actually not greater than equal to, but greater, strictly greater than B, is going to be strictly greater than C. There is no problem in doing that, and so then by the rearrangement inequality, you will get the desired inequality right over here. So A squared plus B squared plus C squared is going to be greater than AB plus BC plus C. If you don't know why, then just check out my video on the rearrangement inequality. That was the previous video on this channel. And you could also do this one by AM-GM. Yeah, we did it in this video, so... Okay, that will be all for this problem. Lovely. Okay guys, so if you like this video, then well, leave a like and subscribe to my channel, because then you will not miss out on any future content I'm gonna be posting. And actually I'm posting every single day, so there is a lot to miss out on. And well, if you like this video, I'm happy, you're happy, everyone's happy. See you in the next one.